Hi guys! This video is part 5 of high-performance driving. In this video, I will explain vehicle balance and acceleration, practice run and elements of high-performance driving. The purpose of high-performance driving, the principle of weight transfer, and the principle of the friction circle and ellipse have been explained in the previous video number E0064 High-Performance Driving Part 1. The principles of spin and sliding, linear and angular momentum, and finally energy conservation law have been explained in the previous video number E0061 High-Performance Driving Part 2. Continuing, centripetal force, rollover, left foot braking, counter steer have been explained in the video number E0062 High-Performance Driving Part 3. Recently, left foot braking for front wheel drive and rear wheel drive, how to drive at the limit, traditional drive line, modern drive line, approach and trail braking have been explained in the previous video number E0063 High Performance Driving Part 4. I have a quiz for you. Which of the following is correct when using the steering wheel to feel the vehicle? Grip the steering wheel firmly with force. The weight of your arms must be placed on the steering wheel. Hold the steering wheel as if you are pushing it. Hold the steering wheel as if pulling. Gently grip the steering wheel with your fingers. Dynamic balance of a vehicle is very important in high-performance driving. High-performance driving is always based on a balanced vehicle. If the vehicle is unbalanced, the driver cannot utilize the vehicle's full capabilities. You cannot slow the vehicle down with full braking power, you cannot negotiate a turn at full speed, and you cannot accelerate the vehicle with full engine power. If the vehicle is not balanced and operated using maximum input, it will cause vehicle movements that the driver does not want. In the last video, we looked at load balance and steering balance for a vehicle's weight distribution, and in this video, we will analyze why a vehicle's load balance and steering balance are important in high-performance driving. Let's analyze the vehicle behavior in a corner and find out how the load imbalance condition occurs. In braking sections, the vehicle's weight is shifted forward, maximizing pitching motion and increasing tire grip on the front wheels. During cornering, when driving on modern line, the turning radius is constantly changing, resulting in inconsistent yawing, roll, and pitch motion simultaneously. Because the vehicle accelerates at full throttle during the acceleration section, the vehicle's weight is shifted to the rear, causing maximum pitching motion and increasing tire grip on the rear wheels. Meanwhile, in the case of the traditional line, the area before A and after B is the same as the modern line. But the turning section between A and B turns at a constant speed with a constant radius. Here, on every line, the point B is the turning point where the turn changes to a straight line and acceleration begins, and you must choose exactly when to accelerate at full throttle. Full throttle acceleration is the moment when the vehicle's roll motion disappears and the vertical load on the left and right drive wheels is equal, thereby achieving load balance. Efficient, high-performance driving is possible only when driving while ensuring vehicle balance. Let's explore this in more detail. In the case of a rear-wheel drive racing car, let's look at what happens when full throttle acceleration is performed while roll motion is in progress at the exit point. For convenience of explanation, we will describe vehicles equipped with LSD, or limited slip differential, on the rear axle. In the corner, the normal load on the outer wheel of the vehicle increases and the normal load on the inner wheel decreases. Therefore, as shown in the picture, when the vehicle turns to the right, the normal load on the left wheel increases and the normal load on the right wheel decreases. In the picture, the vehicle between point A and point B drives on the cornering, so it is driving with roll motion occurring, and the roll motion disappears only after passing point B. In a vehicle cornering to the right, when the vehicle is accelerated during roll motion, the acceleration force of the left wheel, which has a large normal load, is greater than the traction force of the right wheel, which has a small normal load, as shown in the picture on the right, resulting in a moment to turn the vehicle to the right. On the other hand, if you accelerate after passing point B and the roll motion disappears, the acceleration force is equal to the left and right wheels as shown in the picture below on the right, so the vehicle moves straight. From this analysis, you can see that after passing a corner, you must wait for the roll motion that occurred during the corner to disappear before starting full throttle straight acceleration. Let's take a look at what happens if you accelerate at full throttle, while you're in progress at the exit point of a front-wheel drive rally car. The vehicle's weight is moved forward by braking and lateral force is applied by steering, so the driving state of the rear wheels moves from point C to point B on the friction circle, as shown in the picture on the left. Additionally, as the weight of the rear wheel decreases, the friction circle is reduced to a red circle, and since the driving condition is outside the red friction circle, lateral sliding begins. When lateral sliding begins, kinetic energy is lost as road surface friction energy, and after a certain period of time, the driving state moves from point B to point C, yaw and roll decrease, and the vehicle's attitude stabilizes in the straight direction. If you fail to wait for this time and accelerate at full throttle too early, the rear wheel will spin or slide, and the engine acceleration generated from the front wheel will accelerate away from the center of gravity by the distance of the moment arm, as shown in the picture. Therefore, a moment occurs in the vehicle that causes it to rotate around its center of gravity, making it impossible for the vehicle to drive straight. In the case of a rear-wheel drive car, let's look at what happens when full throttle acceleration is performed during a pitching motion on an uneven road surface. When the vehicle is pitching on an uneven road surface as shown in the picture and the normal load on the rear wheels is reduced, and accelerating at full throttle, the friction circle is reduced to a red circle as shown below. Therefore, the driving condition deviates from the friction circle and wheel spin occurs at the rear wheel, making vehicle acceleration impossible. Therefore, we can see that full throttle acceleration of the vehicle should be done after the pitching motion has disappeared. If we summarize the vehicle's behavior regarding imbalance, which we looked at for each section of the driving line earlier, it is as shown in the figure. The explanation will be based on rear-wheel drive vehicles. If you accelerate while roll motion is in progress, the grip of one side tire is greater than that of the other side tire, creating a moment that causes the car to rotate from the side with the greater grip to the side with the lesser grip. Braking creates a moment in the opposite direction. Next, if the vehicle accelerates during motion due to lateral sliding of the rear wheels, wheel spin occurs, and if braking occurs, wheel sliding continues. Lastly, when the vehicle accelerates with the rear wheels lifted in a pitching motion, wheel spin occurs at the rear wheels, which are the driving wheels. If you accelerate or brake when the vehicle's posture is unbalanced, problems will occur. Let's summarize these in turn. Let's look at vehicle imbalance caused by rolling. When a rolling motion occurs in a vehicle, the normal load on either the left or right wheels increases and the normal load on the other decreases by the same amount. When accelerating in this state, a large acceleration torque occurs on the side with a large normal load and a small acceleration torque occurs on the side with a small normal load, causing the vehicle to try to rotate. Even though the steering wheel is not rotated, the torque of the left and right driving wheels is different, and a moment to rotate the vehicle is generated around the vertical axis of the vehicle during acceleration. As shown in the picture, when the vehicle rolls and is tilted to the left, it will try to turn clockwise when accelerating, and will try to turn counterclockwise when braking. The location where this phenomenon occurs during cornering is the exit point, and if you accelerate at full throttle while the roll motion caused by cornering remains, a clockwise moment as shown in the picture occurs, preventing the vehicle from driving straight. Therefore, full throttle acceleration from the exit point should be done after the vehicle's attitude is balanced. Be careful not to get impatient and accelerate to full throttle too early. Let's look at vehicle imbalance caused by yawing. When a front-wheel drive vehicle enters a corner and steers while braking, lateral sliding occurs in the rear wheels, resulting in oversteer. To overcome this, you must countersteer to stabilize the car. In order to achieve full throttle acceleration, you must wait for the rear wheels to end lateral sliding, counter steer to completely end, the steering wheel to return to neutral, and the vehicle's attitude to stabilize for straight driving. Otherwise, if you accelerate at full throttle as shown in the picture, a moment arm is created between the center of gravity and the front wheel acceleration force, generating a steering moment due to the moment to turn the vehicle counterclockwise. The location where this phenomenon occurs when turning is the exit point, and if full throttle acceleration is performed while the yawing motion caused by the turn remains, a counterclockwise turning moment as shown in the figure occurs, preventing the vehicle from driving straight. Therefore, full throttle acceleration from the exit point should be done after the vehicle's attitude is balanced. Be careful not to get impatient and accelerate to full throttle too early. To explain the imbalance caused by pitching, let us consider the case of a rear-wheel drive vehicle. When entering a straight section after passing an uneven road surface, you must wait for the vehicle's pitching motion to disappear in order to accelerate at full throttle. If you do not wait for this and accelerate at full throttle while the load on the rear wheels is reduced due to the vehicle's pitching motion, the rear wheels will spin and the vehicle will become impossible to accelerate. Therefore, when accelerating at full throttle over an uneven road surface after the pitching motion becomes stable, you must accelerate at full throttle smoothly and quickly so that the acceleration force does not deviate from the friction circle. The way to experience oversteer is to gradually increase the vehicle speed along a circle in one direction in a large space. Next, when the vehicle reaches a certain speed, the tire friction noise becomes louder. At this time, you stop accelerating and drive at a constant speed. The driving state at this time is point A. In this state, in a rear-wheel drive car, the rear wheels will be pushed outward with a little extra acceleration, and in a front-wheel drive car, the rear wheels will be pushed outward with a little extra left foot braking. The driving state at this time is point D or point B. Once you get used to the feel of this speed, you can feel the limit of tire friction at point C, just before the rear wheel pushes outward. Point C is the value just before the maximum lateral force and has a value approximately equal to the maximum lateral force. Here, the goal of the practice drive is to feel point C on the graph that we studied earlier in the E0063 video. If the speed is further increased at point C, the lateral force increases, bringing the driving state to point D or point B, and sliding occurs at the rear wheel, pushing the rear wheel outward. By remembering through all senses of the body what the driving state at point C just before the maximum lateral force feels like, and using the maximum lateral force in the driving state at point C during the turning section of actual driving, you should prevent the driving state from moving to point D. You must practice on a uniform road surface with a low coefficient of friction so that you can easily feel the vehicle and prevent accidents. A vehicle with a low center of gravity is recommended. Use a wet road surface that is hard and does not have a high coefficient of friction, a slightly snowy and slippery road surface, or an unpaved flat road surface with small particles. Avoid driving on roads with a high coefficient of friction, muddy roads, sandy or snowy roads, or uneven road surfaces as there is a risk of rollover. While driving at constant speed, you experience oversteer in a variety of ways. Do not try to make large inputs from the beginning. Instead, start with small inputs and as you get used to it, gradually increase the inputs and do a test run. For example, when releasing the accelerator pedal in the first item, you experience a half-stroke release and a full-stroke release. And in the third item, the acceleration is similarly differentiated between input levels such as slow acceleration, medium acceleration, and heavy acceleration, and starts with a small input. After you get used to it, you should try the remaining larger inputs. For all other items, start with small inputs and, as you get used to it, then move to the test drive with larger inputs. The goal of driving here is to feel, remember, and predict with your whole body the functional relationship between pedal input and output, which is indicated by the amount of oversteer. In a rear-wheel drive vehicle, the first, second, fourth, and fifth driving states are point B, and the third driving state is point D. Sixth, the driving state of left foot braking depends on the magnitude of braking torque and engine torque. If oversteer occurs during test driving, counter-steer as described above and quickly steer the front wheels toward the target line. In vehicles of all drive types, the sixth method requires special care because traction and braking are inputs simultaneously. If done incorrectly, it may strain the powertrain and cause it to bend or break. Racing cars that allow large left foot braking at full throttle have sufficient powertrain strength, but street cars do not. So you should never apply large left foot braking at full throttle in street cars. Because the front and rear wheels are already using all their friction for lateral force, even slight acceleration or braking pushes those wheels outward. Therefore, when practicing along a certain circle as shown in the picture, there is no need to give a large input to cause oversteer. You should never press the brake all the way while pressing the accelerator pedal. You should press it lightly, as much as necessary, for an appropriate amount of time. On vehicles equipped with the aforementioned BOS system, press the brake pedal lightly several times in short bursts. This is a particularly sensitive area and requires a lot of training to get a good feel for the car you are driving. If oversteer occurs during test driving, counter-steer as described above and quickly steer the front wheels toward the target line. Let's explore the elements of high-performance driving. First, you need to feel your car you will be driving by feeling and predicting the friction circle of your car. This part of feeling the vehicle is most important in high-performance driving. Keep your eyes on the direction you want to go and check for obstacles and driving paths. In other words, decide how to drive. In a rally or drift race, you must secure the amount of entry momentum that suits your driving method. In racing, you decide when to start braking. You should delay the start of braking as much as possible. Keeping your eyes on the next driving event, you initiate vehicle maneuvers boldly and quickly but smoothly, using the brake pedal, accelerator pedal and steering wheel exactly as needed. At the exit of a curve, wait until the vehicle's attitude is balanced before full throttle acceleration. Let's look at these one by one. Let's learn how to feel a vehicle in relation to the friction circle. A vehicle's tires are like human shoes. When a person walks, the pressure coming through the shoes can be felt at each location on the sole. The calves and thighs are the suspension, and the upper buttocks are like the body of the car. The angle of the calf seen from the front is similar to the camber angle. In a car, there are wheels, hubs, and suspension between the driver and tires. The driver must feel the signals coming from the road surface through these. In particular, you must have a good understanding of the suspension structure to feel the car better. In the picture, the front foot carries a lot of weight, so the friction circle is large, and the back foot has less weight, so the friction circle is small. The front foot has a large friction circle and plenty of available friction, while the back foot has a small friction circle and is used close to maximum friction, so there is almost no available friction. Therefore, you can accelerate, stop, and turn around your front foot, but this is not possible with your back foot. In this way, people instinctively feel and predict friction circles on the bottom of their feet while walking. Likewise, feeling the vehicle means feeling the friction circle of the vehicles for wheels and predicting how the friction circle and driving state position will change when steering, accelerating, or braking. Drivers must be able to predict the vehicle's driving conditions and feel feedback from the road with their whole body. In order to predict the driving state of the vehicle in response to the driver's operation, Drive the car a lot in various driving environments and when acceleration, braking, steering, and a combination of these are input to the vehicle, the road surface feedback is reflected in each part of the body. You must clearly remember how you feel and clearly establish the functional relationship between the input and the output of your body's sensors. The sensors in my body include my fingers, soles of my feet, stomach, heart, kidneys, head, back, stomach, buttocks, thighs, and calves. The important thing here is to understand the vehicle's system and structure, so that the vehicle's driving condition can be accurately predicted and road feedback can be accurately felt. In the vehicle system, there are powertrain, brakes, and tires, and the structure includes weight distribution, suspension, and aerodynamic equipment. In particular, clearly understanding and remembering the structure of the suspension, imagining their movements when the vehicle accelerates, brakes, turns, and drives on uneven road surfaces, and predicting tire grip are very helpful in feeling the vehicle. What information is needed to feel the vehicle? As seen earlier, in order to feel the vehicle, you must have a good understanding of the driving environment and vehicle systems and structure. The driving environment includes road surface friction coefficient, wind direction, and wind speed. The vehicle structure includes aerodynamic equipment, vehicle weight distribution and height of center of gravity, vehicle dimensions and suspension geometry, and the vehicle system includes tire characteristics, relationship between braking force and brake pedal effort, and relationship between engine power and accelerator pedal stroke. Let's look at each of these in turn. The characteristics of tires are a very important factor in feeling the vehicle. As explained earlier, the maximum lateral force that can be extracted from a vehicle does not increase proportionally with the increase in the normal load acting on the tires, but increases less than the increase in the normal load. As shown in the figure on the left, when the normal load increases by 1 kN from 4 kN to 6 kN, the increase in lateral force FL2 is less than FL1. Additionally, as the vehicle speed increases, the lateral force corresponding to the same lateral slip angle alpha becomes smaller. This means that as the speed increases in a corner, the friction circle decreases, and thus the maximum lateral force decreases. Regardless of normal load or speed, an experienced driver should be able to feel the changing maximum lateral force with his or her entire body, but knowing the above-mentioned knowledge will greatly help a driver feel the vehicle and predict the grip of the tires on the road. Since the friction coefficient varies depending on the type and condition of the road surface, the size of the friction circle also changes. Accordingly, the maximum values of braking force, acceleration force, lateral force, and self-aligning moment also vary. Since the force that initiates sliding and spinning varies depending on the size of the road surface friction coefficient, the vehicle's feedback varies depending on the type and condition of the road surface. Therefore, in order to drive using the vehicle's maximum friction under given road conditions, you must develop a sense of the vehicle's feedback through sufficient practice in each applicable condition. As before, regardless of the type and condition of the road, an experienced driver should be able to feel the changing maximum lateral force with his or her entire body, but knowing the above-mentioned knowledge will greatly help a driver feel the vehicle and predict the grip of the tires on the road. Let's learn how to feel normal load on aerodynamic devices. Feel the aerodynamic force by changing the speed. To feel the effects of pure aerodynamic equipment, it is best to drive when there is no wind. Depending on the driving speed, feel the aerodynamic force acting on the front wheels and the aerodynamic force acting on the rear wheels, and feel whether they are well balanced. As explained in the video earlier, it is important to have a balance in which all wheels, front and rear, press on the ground at the same size. If the load balance between the front and rear wheels changes depending on the speed, The driver will experience great confusion in driving the vehicle. Let's take a look at the vehicle's weight distribution. As we saw earlier, a vehicle's weight distribution affects its cornering ability. As shown in the figure, let's consider a case where the vehicle's center of gravity is closer to the front wheels than the rear wheels. So the normal load on the front wheels is greater than the normal load on the rear wheels. As explained earlier, the lateral force increases at a small rate compared to the rate at which the vehicle's normal load increases. So compared to a vehicle in which the normal load on the front and rear wheels is equal and the load is balanced, a vehicle without balance in which the normal load on the front and rear wheels is not equal, and the load is unbalanced, has smaller maximum lateral force regardless of whether the normal force sum of front wheels is larger or smaller than that of rear wheels. Therefore, when the vehicle weight is the same, a car with the vertical load distributed equally between the front and rear wheels can handle a greater lateral force than a car with an uneven weight distribution, so it can pass through the corner section at a faster speed. The picture on the right shows the friction circle of the entire tire, including the front and rear wheels of a load-balanced vehicle and a load-unbalanced vehicle. The friction circle of the load-unbalanced vehicle, shown in red, is smaller than the friction circle of the load-balanced vehicle, shown in blue. Therefore, a load-balanced vehicle can handle greater lateral forces than a load-unbalanced vehicle. Let's look at the effect of center of gravity height. A vehicle with a high center of gravity has larger roll and pitching motions for the same input than a vehicle with a low center of gravity, and it takes more time to stabilize. When a corner section ends and a straight section is entered, if you accelerate at full throttle while the roll motion is not stable, a yaw moment will occur in the vehicle, so the vehicle's attitude must first be stabilized before full throttle. Additionally, if the stiffness of the stabilizer is high, the inside tire will come off the ground during cornering. When this phenomenon occurs, the overall lateral force value is reduced, so the speed through the corner is reduced, and the lap time increases. Vehicle dimensions affect the increase or decrease of normal load on the front and rear wheels, or inner and outer wheels, during driving. The longer the wheelbase, the smaller the increase or decrease in normal load on the front or rear wheels due to the same acceleration or braking force. And the smaller the wheelbase, the larger the increase or decrease in normal load. Wheel track affects the increase or decrease of normal load on the inner and outer wheels when cornering. The larger the wheel track, the smaller the increase or decrease in normal load on the inner or outer wheels due to the same lateral force. And the smaller the wheel track, the larger the increase or decrease in normal load. When accelerating a vehicle, a squat phenomenon occurs where the rear part of the vehicle is lowered, and when braking, a dive phenomenon occurs where the front part of the vehicle is lowered. Squat and dive phenomena are pitching motions of the vehicle body, and their magnitude is determined by suspension geometry, location of center of gravity, and wheelbase length. Drivers must physically feel the relationship between these pitching movements and pedal input when accelerating and braking the vehicle, and know the maximum pedal input stroke that does not cause sliding or spin. In other words, you must remember the maximum acceleration and braking operation conditions that do not exceed the limits of the friction circle. During cornering, the vehicle's body becomes higher on the inside and lower on the outside, causing a roll motion. The roll motion of the vehicle body is scaled by the suspension geometry, the location of the center of gravity, and the wheel track width. Drivers must physically feel the relationship between roll motion and driving speed during the vehicle's cornering, and know how much torque is being generated. You must feel the lateral force during cornering to determine the maximum accelerator and brake pedal input that will not cause sliding or spinning. In other words, taking into account the lateral force that occurs when turning, maximum acceleration, or maximum braking must be achieved without exceeding the limit of the friction circle to enable high-performance driving that utilizes the vehicle's full potential. Suspension geometry affects a vehicle's body roll. The longer the vertical distance between the center of gravity and the roll center, the greater the body roll. I will explain the roll center in the next video. You should try to memorize the wheel alignment values of the camber, caster, toe, and kingpin offset of the vehicle being driven, as well as the suspension stiffness values of the shock absorbers, stabilizer bars, and springs, and these must be remembered by connecting them with the driving feedback that occurs when accelerating, decelerating, cornering, and being forced by any of their combination. By memorizing these feelings, you can predict how the vehicle will behave when these values are changed. When changing suspension settings, you must predict how your vehicle's performance will change before driving. You can predict in advance whether the tendency to oversteer or understeer will increase, and whether steering accuracy will improve or worsen. If the predicted and driving results are different, you need to think about why and identify the cause. Through this process, your skills will gradually improve and your sense of the vehicle will become increasingly sensitive. It is also important to keep careful records of this entire process. Keep detailed records of everything including wheel alignment, data on each suspension part, and driving results. Let's learn about braking force and brake pedal effort. The driver's body must accurately feel the brake pedal effort as input and the braking force as output in a functional relationship. Braking is most sensitive and difficult in high-performance driving. If you can use the maximum braking force corresponding to the given lateral force, while delaying the braking point as much as possible in the corner section, the acceleration section can be extended and the driving time can be shortened to the maximum. In order to effectively perform trail braking as described above, when lateral force and braking force act together, it is necessary to know how much the brake pedal should be depressed to avoid wheel sliding and use the maximum friction force of the tires. Let's learn about acceleration force and accelerator pedal stroke. The driver must also accurately feel the accelerator pedal stroke as input and the acceleration force as output in a functional relationship with the driver's body. In a rear-wheel drive car rally race, in order to pass a curve using rear-wheel spin when lateral force and braking force act together, you need to know the accelerator pedal stroke and application time to produce an exact degree of rear-wheel spin bring about oversteer, as necessary. Additionally, when the vehicle's attitude is unstable due to rolling, yawing, or pitching motions, you must know how much the accelerator pedal should be depressed to avoid generating a yawing moment in the vehicle. The most important thing is to be able to feel your car and control your car based on what you feel. In the movie The Transporter, Jason Statham agrees to transport a hostage by saying, "I will drive in my car." Vin Diesel talks about 3 things about high-performance driving in the movie Fast and Furious. Firstly, feel the car. Secondly, keep your eyes on the direction you want to go. Thirdly, fly. The landing site for the Vin Diesel's car was another road crossing below from the intersection. Only when you are familiar with your car can you control it and drive at high performance. When accelerating or braking, your body needs to remember the connection between the pedal stroke and the amount of weight transfer. When accelerating during cornering, you need to remember at what speed and how much you have to press the accelerator pedal to cause sliding. Remember to associate how the vehicle reacts with the amount of engine braking during cornering. In addition, when the size and time of all vehicle operations are called input, and the vehicle behavior in response is called output. If your body remembers their functional relationships, you can drive at high performance to the maximum ability of your car. When you feel the car, You should feel it with your whole body. You should feel the vehicle with all parts of your body: hands, feet, shoulders, stomach, thighs, buttocks, stomach, heart, etc. Among these, the most important areas are the fingers and front of the feet, which are in direct contact with the vehicle's operating parts. The thing to be careful about here is that you should not apply force or put weight on the area that touches the vehicle with your hands. The forces and weight applied to the vehicle's operating system act as dampers, attenuating or distorting the response of the system's stiffness and weight. You must relax your fingers and hold the steering wheel slightly to feel the vibration and force coming through the tires. In the heel and toe technique, the brake pedal is operated with the front of the foot because the front of the foot feels better than the side of the foot or the heel. Unlike driving force, braking force requires fine-tuning in high-performance driving, making the brake pedal much more difficult to control than the accelerator pedal. If you reverse the heel and toe motion and operate the brake pedal with your heel and the accelerator pedal with the front of your foot, you will see why you should operate the brake with the front of your foot. If you hold the steering wheel as lightly as possible with your fingers while driving, you can clearly feel the road input coming through the tires. Try driving through speed bumps with different angles of entry, and drive at low, medium, and high speeds under various road conditions, such as uneven road surfaces and turning sections. Also, feel the feedback from the steering wheel when braking or accelerating. It is important to drive a lot and train your hands to be sensitive so that you do not miss the slightest feeling that comes through your hands. If you drive for enough time under various driving conditions and memorize the feedback you receive through your fingers, you can predict the feedback when driving on the same road surface. You can feel all the feedback coming through the tires, including on-center steering performance, driving conditions on the friction circle, torque steer, and bump steer. Let's learn how to feel the vehicle through the steering system. The graph in the picture shows how the vibration, acceleration, velocity, or displacement of the steering wheel changes over time, and shows the output signal when the steering wheel is held as lightly as possible using both fingers. In order to properly understand the vehicle's driving condition, it is important to feel the road surface input coming through the tires. If you apply too much force or hang on the steering wheel, the system characteristics of the steering wheel will change, causing the sensation in your hands to feel distorted. Let's take a look at how signals can be distorted one by one. Let's find out what happens when you apply force to the steering wheel. When the driver becomes tense and applies force in the direction of pushing or pulling the steering wheel, the original vibration signal of the steering wheel is attenuated and becomes smaller. If this happens, you may miss the subtle feedback coming in through the steering wheel. Additionally, because the driver's force continues to vary over time, it becomes impossible to consistently feel road feedback from the steering wheel. Therefore, applying more force to the steering wheel than necessary for steering prevents the driver from feeling the car properly. In order to feel the car consistently, you must hold the steering wheel with the minimum amount of force required to steer and feel the road feedback coming through the steering wheel. Let's find out the effect of arm mass. Placing the mass of the arm on the steering wheel as shown in the picture adds the mass of the arm to the steering wheel, distorting the steering system. When the mass of the arm is added to the steering wheel, a dynamic damping effect appears, as shown on the right. If the original steering wheel was the system shown above on the upper right with a single resonant frequency, as the mass of the arm is added, the magnitude of physical quantities such as the acceleration of the steering wheel decreases, and the resonance frequency of the steering wheel changes into 2 and becomes smaller, as shown in the red line in the picture below. Because the frequency characteristics of the system act as a bandpass filter, The size of the road surface feedback is distorted depending on the frequency and is transmitted to the driver. Therefore, drivers cannot consistently feel road feedback. In order to feel accurate road feedback, you must not let the mass of your arm hang on the steering wheel. If the driver becomes tense and grips the steering wheel harder than necessary, this dampens the steering system's natural vibration system and reduces the amount of road feedback. If this happens, you may miss the subtle feedback coming in through the steering wheel. Additionally, because the driver's force continues to vary over time, it becomes impossible to feel road feedback at a consistent magnitude through the steering wheel. Therefore, gripping the steering wheel with more force than necessary to steer prevents the driver from feeling the car properly. In order to feel the car consistently, you must hold the steering wheel with the minimum amount of force required to steer and feel the road feedback coming through the steering wheel. Once you get a feel for your car through regular practice, start the actual high-performance driving. First, look at the direction you want to go, check for obstacles, and then decide on a driving path that sufficiently avoids the obstacles. Once you have your driving path determined, decide how you will drive. In the case of the rally race pictured here, in front-wheel drive, left-foot braking can cause oversteer to negotiate curves, but there are more options to choose from in rear-wheel drive vehicles. You can also use left-foot braking and rear-wheel drive spin. Entry speed varies depending on each method. Hand brake turns are not used in racing or racing. This is because it is difficult for the driver to feel the braking force from the hand brake, making control difficult. It is difficult to control the braking force provided by a hand brake to exactly the amount required. Additionally, hand brakes are not recommended for racing or rallying, as they interfere with the time it takes for the fingers of both hands to keep feeling the tires. Depending on how you drive, you must secure the necessary entry momentum. Entry momentum provides the vehicle with the energy to overcome road friction and keep moving during high-performance driving. In this case, the road surface friction force is the road surface friction force generated by the brakes and the road surface friction force caused by the yawing motion, and an appropriate amount of momentum must be secured to overcome these forces and allow the vehicle to move as desired. If the momentum is too much, the vehicle will move excessively and deviate from the desired path, while if it is too little, the vehicle will stop. Therefore, you need an appropriate amount of momentum depending on how you drive. If you have accelerated to the maximum on a straight section to increase driving speed before entering the next corner, you must brake to reduce the vehicle speed to Vs, the maximum possible speed for passing the corner. To achieve this, the full stroke braking starting point beginning from the straight section must be delayed as much as possible so that the speed at position S is versus. If VQ is the correct full stroke braking start point, if you start braking too early at point P, the braking time will be longer and the lap time will be delayed, and if you start braking too late at point R, the vehicle may deviate from the course or wheel sliding may occur due to insufficient braking time, which also results in a slower lap time. Therefore, maximum braking must start at the exact point Q and end at point S. In this way, accurately braking to achieve the desired vehicle speed at each point is very difficult without much practice. Your eye should always be on the next driving event. In high-performance driving, the driving environment keeps changing without enough time to think. So if you drive while only looking at the driving environment right in front of you, you will not be able to cope with the next driving environment. For example, in the picture, if the driver of a vehicle in a straight section only looks at point A, after passing point A, there will be no time to think about what to do at point B. After passing point B, there is no time to think about how to deal with point C. If you drive to point E in this way, your thinking and driving operations will become dizzy and you will waste valuable time. Experienced drivers keep the entire course in their head, draw a big picture of driving, and then keep their eyes focused on the driving environment one step ahead. For example, in this picture, an experienced driver has a big picture of driving for the entire course from A to E in his head, and on the straight section I before entering the corner, his eyes are on B rather than A. When you pass A, you look at C, not B. When you pass B, you look at D, not C. When you pass C, you look at E, not D. The head thinks about the next driving environment, and the muscles solve the current driving environment. In this way, when the surrounding driving environment flows like a current panorama, the muscles in my body automatically respond and drive, and my head goes one step ahead and prepares commands for how to move my muscles. Now that you have the necessary momentum, operate the vehicle quickly, smoothly, and accurately. If the operation is delayed, the appropriate timing may be missed, resulting in confusion in responding to the subsequent driving environment. Using the steering wheel, clutch, brake, and accelerator, the determined high-performance driving method is implemented. Doing it quickly does not mean that you have to use all your strength to complete the driving maneuver. Driving operations must be done on time with quick movements, and the movements must be smooth. If the driving maneuver is not performed smoothly and exactly as required, the speed may be too high, resulting in a large amount of unwanted spins or sliding, resulting in longer lap times, or, conversely, the speed may be too low, resulting in longer lap times. When you reach the exit of the turning section with quick and smooth driving maneuvers, you must wait until the vehicle attitude stabilizes and the friction of the rear tires recovers. One of the biggest causes of failure in high-performance driving is accelerating without being able to wait. When looking at left foot braking in a rally car with front-wheel drive, the braking force is applied to the entire vehicle, so the driving state moves from point C to point B, as shown in the picture on the left. Additionally, as the weight of the rear wheel decreases, the friction circle is reduced to a red circle, and since the driving condition is outside the red friction circle, lateral sliding begins. When lateral sliding begins, kinetic energy is dissipated into road surface friction energy, and after a certain period of time, the driving state moves from point B to point C, and the yawing and rolling motions are reduced and the vehicle's attitude becomes stable. If you fail to wait for this time and step on the accelerator pedal too quickly, the front wheels will accelerate while the rear wheels spin or slide, creating a moment that causes the vehicle to rotate around its center of gravity, making it impossible for the vehicle to go straight. When the friction of the rear tires is restored and the vehicle's attitude is stable, accelerate smoothly and quickly and drive in a straight line. What you need to remember here is that full throttle acceleration must be done after the vehicle's attitude is stable. Otherwise, a yawing moment will occur, causing problems with the vehicle's direction and lengthening the driving time. Let's find the answer to the quiz. Which of the following is correct when using the steering wheel to feel the vehicle? The answer is number 5. Gently grip the steering wheel with your fingers. Let's summarize the contents. The purpose of high-performance driving, the principle of weight transfer, and the principle of the friction circle were explained in part 1 of video number E0060. Principle of spin, principle of sliding, inertia and momentum and energy were explained in part 2 of video number E0061. Principle of centripetal force and rollover, weight distribution and lateral force, understeer, oversteer, countersteer, engine map, left foot braking, Pitching and roll motion related to friction coefficient were explained in part 3 of video number E0062. Left foot braking and friction circle, driving at the limit and friction circle, driving line. Trailing and approach braking were explained in part 4 of video number E0063. In this video, vehicle balance and friction circle are explained. If you accelerate at full throttle before the vehicle is balanced, a yawing moment will occur and prevent the vehicle from moving straight ahead. Full throttle acceleration should begin after pitching, roll, and roll motion are disappeared. The practice of high-performance driving was explained. Increase the vehicle speed to the limit of the friction circle along a circle with constant radius in one direction in a large space. Try out various driving techniques such as accelerating, braking, engine braking, and steering wheel operation. With small manipulations, feel and remember the sensation of the vehicle's movement and maneuverability. As increase the amount of control, feel and remember the sensation of the vehicle's movement and amount of control. Predict and manipulate the size and attitude of vehicle movements. The elements of high-performance driving can be summarized as follows. Feel your car. Keep your eyes on the direction you want to go. Check for obstacles and determine driving path. Get the necessary amount of momentum. Delay the start of braking as much as possible. Keep your eyes on the next event. Manipulate quickly, gently, and exactly as needed. Wait for balance. Accelerate. If you watch the previous videos, you can easily understand upcoming videos. In video number E0062 of High-Performance Driving Volume 3, which is Principle and Theory Part 3, I explained weight distribution, lateral force, how to overcome understeer, how to overcome oversteer, countersteer, engine map, left foot braking, friction coefficient, and pitching and roll motion. Recently, in video number E0063 of High-Performance Driving Volume 4, which is Principle and Theory Part 4, I explained left foot braking and friction circle, straight ahead and cornering for front-wheel drive and rear-wheel drive vehicles, driving at the limit and friction circle, traditional and modern driving paths, and trail braking. The next video is part 6 of high-performance driving. I will explain suspension setup. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.